And it's up here somewhere. Didn't I have it up here? And now you got me distracted, asking about streaming and videos. Oh, there it is. Is that it? Yeah, there it is. Okay, so there's two things you have to do is first of all check that you satisfy the hypotheses of either mean value theorem or Rolle's theorem. And of course, there's no way for WebAssign to be able to evaluate whether you actually did that. And then the second thing is to actually find the point that satisfies the theorem. So did you have any trouble with any of these? Or are there questions about like what the difference is between Rolle and mean value? Well, no, I won't even say it because I don't want to confuse anyone. So Rolle's mean value, you could do this, and you know that you have to check. So what is it that we have to check? Let's see. Let me do this first one just to see how it goes. Whoops, click, move, up. No, I don't like that one. Okay, I like this one. Oh, 4 and 5? There's no 5. Yeah, 3 I like. 3 I like. So let's just talk about 3, because 3 has everything. Oh, welcome. I'll adjust the attendance situation for both of you.
Mind?
What?
I don't want to be gray.
He doesn't want
Yeah, I'm going to fix
that.
that. Yeah, I was going to fix it when I fixed it. Yeah, no
I'm being temperament though.
Okay, I could put you to temper mode,
Oh yeah.
and you use up one of your temper modes. Okay, because you're temporarily remotely from where you should be, which is right there behind that. Okay, so
I think you should be in the back of the picture.
it says, does this function satisfy the hypothesis of the mean value theorem? Let me remind you what those hypotheses are. Number one, you want to make sure that your function is continuous, because if it's not continuous, you could easily thwart the mean value theorem. Mean value theorem says that somewhere between 1 and 5, there will be a point where the slope of this function is the same as the average slope. But if you have discontinuity, then you could not have that be the case. So continuous is number one. Number two, differentiable. It means that the slope doesn't come to a point in between 1 and 5. And then that's pretty much it. So let's see, this one is yes, because this is continuous and differentiable, so you're good. And then you can find the value of C by computing the average slope. The average slope will be the natural log of 5 minus the natural log of 1 over 5 minus 1. And then do the derivative of this and set it equal to that fraction and solve. So anyway, that's just want to make sure that we had the quick overview, since some people came in saying that they had no idea what we were doing. But if we don't have any questions, we can move on to the quiz. Yeah, what do you think, Jackson?
So I did them all in little problems, but I didn't actually realize that mean value theorem and Rolle's theorem were different.
Oh, yeah, they aren't. So that's what I was going to say, then I hesitated to say, is that basically, you know what a square is? Yeah, you do. And you know what a rectangle is, right?
Mm-hmm.
Every square is also a rectangle. Isn't that weird? So same thing here. Every Rolle's theorem is also a mean value theorem. It doesn't go the other way, but it's a similar relationship. So the Rolle's theorem is basically the mean value theorem.
So was there only one way to solve these?
Mm-hmm.
Was there only one way to solve these?
Yeah.
Okay.
Sorry, I said mm-hmm, but it came out as I don't know what it came out as. So, thanks. Yeah, so, yeah, Rolle's theorem. Why even call it? I guess because historically it came before the mean value theorem, but it's really the same. It's just mean value theorem is an expansion.
Well, mean value theorem, you don't have to check if A and B are equal, right?
No, but you, okay.
You do on Rolle's.
Yeah, and so that's like the square and the rectangle. You know, a square, you have to check to see that the sides are equal. Whereas a rectangle, you just check that they all are right angles. Yeah, so, but yeah, you're right. It is just one theorem, essentially. And actually, you could ignore the checking to see if the two are equal with Rolle's theorem, as long as you don't invoke Rolle's theorem, as long as you just say, oh, it's just the mean value theorem. So, yeah. I know, it's super confusing. Why in the world do we even care? Yeah, it's amazing how when I grade these AP exams, I do this every summer, how many students get these two mixed up. And yeah, I don't really care, to be honest. And I feel like I'm like, oh, you wanted the one that has WD-40.
Oh, yeah.
Yeah, sip it.
Delicious.
What do you think? Got it? All right, welcome. I'll fix that in the picture, don't worry. No, sweet time, huh? So you can either use rolls, no, don't use rolls. Okay. Tense. Fix it. Well, Jarrett, you'll have to let us know if you get an email. I just fixed, to say that it was fixed. You don't have to do it. All right, you're probably already done, so I'm goofing around up here. I'm gonna give you a couple of pieces of paper, and if you aren't done, you can get done. So you get two. Everyone gets two.
Everyone gets two?
I know, I'm being so generous.
I feel so happy. I don't think I've ever done this before.
About 2 pieces of paper?
Yeah.
I should have made them front and back as well.
That would have been even cooler.
Well, yeah, it would be more efficient. I've got lots of stuff. You should be. You want that? Nice.
I also want to use it.
Okay. Yeah, okay. Is this the class that needed the WD-40?
No.
Squeaky? Another class, must be Calc 2, they're all complaining about the squeaky chairs.
I mean, these chairs
I
are
think
all.
where's the cherry?
Mine's okay.
Well, that's why I brought it. let's share it with the class. So look at that, amazing.
There's, I understand someone who brings
Brings what? Everywhere? A student? Nice. I had a student who was very irritated by squeaking, and this is a dozen years ago. And there was another student that was similar to Jarrett who knew that she was irritated by squeaking, and so he would just sort of get his chair to squeak just a little bit. You know you would, wouldn't you, if someone really had a problem with this? And so she came in at like a half hour early one day. I came in and she had all it was these tablet desks upside down, and she was dealing with them, and by the time she got done, there were no squeaks. It was amazing. So she was like, I'm just gonna fix this. This is probably 15 years ago. This is a long time ago. The building, actually the room that I was in, it's not even a classroom anymore. So.
Which room?
It's basement of the campus center. When you go down the stairs, there's a room to the right. I don't even know, is it commuter lounge now?
The old SBA lounge? Yeah.
Like as you
Yeah,
go
when
down,
walk into the doors,
so you
right
got
there.
like motherboard in front of you. There's like a room. Yeah, that used to be a classroom. It's horrible. No windows.
You talking about in the library?
Yeah, in the library.
Yeah, that's.
Oh, the ERC
yeah.
room?
Oh,
Yeah,
that's the commuter room?
Yeah, I never go there though.
Yeah, the computer, commuter lounge.
I wouldn't recommend.
Yeah,
Yeah.
there's
You're
no
talking
signal down there.
No Wi-Fi?
Well, there's Wi-Fi, but there's the
Oh.
school's Wi-Fi,
Yeah.
but there's no
Are you
like
talking about-
cell phone service
You
down
talking about
there.
in the library?
Yeah, in the library.
Like
go down
where the motherboard is.
Next to
Yeah, so
motherboard.
there's the ERC
There's
room.
no signal.
Yeah, there's none.
It's the ERC.
Like I've
That's so
tried
interesting.
every corner of the room, there's nothing down there.
You know,
So I just stopped going
the
down.
commuter lounge used to be
There's a building,
Yeah, there's like,
yeah,
it's
but
like
I
a
wouldn't
barn.
recommend.
The barn.
Oh.
Why? What's wrong with that one?
Dead people.
There are dead people?
No, there's some talking, yeah, I wouldn't recommend going there.
Why?
I do talk to college.
I'm so curious. I'm gonna go check it out. 'Cause, okay, so
Sorry, I by myself.
really?
Yeah.
I'm so curious now. You know that Jarrett's going in there right after class.
What are we talking about?
Wherever it is, Leanne's scared of a building.
Yeah, can we all go right
Yeah,
now?
we should go right now.
We have to do this,
We
so,
should do calculus on the way.
I wanna know why we have drafts in front of us.
Yes.
I mean, learn
I know.
You can teach on the way, just bring your.
okay,
laptop.
so we're, yeah, we've gotta get to tables, graphs, asymptotes. And so I think this is the table that Claire, or it's not quite like this.
We're getting closer to
Yeah.
that big table.
Yeah, I used to have a big table like that, and I gave up because I knew how daunting and scary it was. So this is about as complicated as it's gonna get, is this table.
Oh, generous.
Wait, we're leaving now? What's going on?
No, I'm
Okay.
just setting up
Hmm.
so I can start writing.
Okay. Anyway, getting back here. So the first of all, I need to explain why we have this graph in front of you, and then we'll get to it. So one of the applications of knowing about derivatives is understanding how graphs look. So you could sketch graphs. Back in the olden days, when we didn't have nice graphing calculators, that you could just say punch in your function and have it say, oh look, that's that beautiful graph. We used to have to actually think about what the graph was going to look like. And that's what we're hoping you do here, because not only does it help you with the graphing, but it helps you with the applications later on. So let's do the graphing first. So the derivative, derivative, oh yeah, here it is, it's just blank. Derivative, what do you think of when you think of derivative? Wait, who said it? Slope? You were whispering it, thank you. So slope. Slope is derivative. When you think of a graph, slope is derivative. So that's what the derivative is. It's the rate of change. So that's what we're going to do, is we're going to talk about increasing and decreasing. And this is the technical definition of the increasing and decreasing. However, in practice, what we'll do is we will just compute the slope. And when the slope is negative, you're decreasing. When the slope is positive, you're increasing. So far, so good? Sure. Next. Let's see. Let's take a look at an actual example of this. So here, this one is the one we want to skip this slide. Where's my mouse? There it is. Not that one either. That's the one. So let's take a look at this example. And you've noticed that on your, let's get rid of Okay, on your piece of paper that I gave you two of, you have at the top, there's two graphs there, and at the top there is a little thing that says F. What you want to do is copy F into the F on that paper. And if you're worried about wasting the piece of paper, don't worry. I have this piece of paper, this template online. Not that it's any good. I'm really not that proud of it, but I thought someone might want to use this. So here's the idea, is you're going to do this right there. So I've got my function. You've got it written in there. Now what we're interested in is I want to know where this thing is increasing and where this function is decreasing. And the way we're going to find that out is we're going to use the first derivative, the slope. The slope is going to tell you whether it's increasing or decreasing. Let me just pull up my people, because I know you all know how to do this derivative. But go ahead and do the derivative. Write it there on the next line, and then we'll pick some people to do this. So here we are. So Jackson, you know the derivative of this function, don't you?
Actually, no.
Oh, you can do it. Just yeah, just do it one term at a time. What's the derivative of x cubed? Excellent. And then what's the derivative of x squared?
So the first one just stays over 3.
Yeah, the 3, yeah, you could use the quotient rule if you wanted to, but it would be silly. Yeah, just do it, because the 3 is a constant. It's kind of like, yeah, it's kind of like if it was 5 times x cubed, you would just do the derivative, multiply. So it's like 1/3 times x cubed. So yeah.
Oh, okay.
Oh, did everyone want to do the quotient rule there?
Yeah.
That's not wrong. You would get the right answer. It's just a lot of work. But anyway, go ahead, Jackson. What's x squared? Yeah, very nice. See, I knew you knew it. So there it is. So there's the derivative. Now, in order to figure out the slope, like where this is increasing or decreasing, what we're going to do is we're going to do this. We're going to find the critical numbers, and then we're going to determine whether you're going up or down between the critical numbers. You see, the critical numbers are the only place the slope can change from positive to negative or negative to positive. So that's sort of the goal here, and that's why the very next thing on my chart is critical points or critical numbers. So we need to find these so-called critical points or critical numbers. Claire, what do I have to do to this to find the critical numbers? Oh, it's set the derivative equal to 0, and I'm going to get rid of the 3's because they were causing so many problems as it is. Go ahead and solve that if you haven't done it already. Some of you are done with the entire page and have the graph, and it looks beautiful. All right, Colton, what did you do?
I got 0 and 2.
Okay, 0. How did you do that?
I factored out an x.
Okay, very
and I
good.
got negative x plus 2.
That's exactly right. Okay, so x equals 0 and x equals 2. So remember, those are the places where the slope is 0. So you're either at a maximum or a minimum. And those are the only place where the slope is 0. Now I suppose we should at least make a nod to the fact that this could be, no, it's never undefined. But you should check that. Check to see if you have an undefined point, because if you do, then you have to deal with it. But for this one, you're okay. Okay, so far so good. Next thing we're going to do to figure out the slope is you determine the sign of f. F prime. Let's actually just do it. It's easier to do than to say, apparently. So we'll get to that in a minute. Here we go. So down here, I've got this little thing. I know this is a little out of order, but I've got this little number line. And on it, I have labeled f prime. So what you should do is put x equals 0 and x equals 2 on this number line. This is just a tool to help us figure out the, what's going on with the slope. So here we know that the slope is 0 at those 2 points. And so I need to pick points in between and on the left and right. So I have 3 intervals that I need to worry about. Those 3 intervals are from negative infinity to 0, and then from 0 to 2, and then from 2 to infinity. I need to know whether the slope is positive or negative on each of those intervals. And so it's up to you. You can pick any point you'd like on each of these intervals. I'm just going to put a little X here, or I guess just to indicate that I'm going to pick a point. You're going to pick a point. But Sam, what point would you like to use for the first interval? That's the one from negative infinity to 0. Any number works, but you can pick, so it's up to you.
Negative infinity.
Okay, any number, and negative infinity is a concept, not a number.
-7.
Okay, -7 works as well. Okay, so what we're going to do is we're going to plug that -7 into this derivative up here, which is, I'm going to use this for my derivative. In fact, I'm just going to copy this as, whoops, trying. Because I can, I'm going to copy and paste. There. Okay, so when I plug -7 into that, I'll do this one for you. So plug -7 in, since Sam picked it, I'll do it. I get negative times -7 squared plus 2 times -7. So that's going to be negative times positive 49, because -7 squared is positive 49, plus 2 times -7. You could always do this on your calculator, and you end up getting negative 63. Yeah, negative 63 is the final answer. But all that really matters is that it's negative. Whoops, just a minute. Negative 63. So I really don't care about the 63. All I really care about is negative. And what that tells me is that over here, the slope over here is, in fact, negative 63 is pretty steep. But the slope is negative. So this function will be decreasing, and then it hits this point. So let's see what happens after that point. You might say, oh, it's going to increase. Not necessarily. Let's not be too hasty. Okay, so next we're going to pick a point between 0 and 2. And who gets to do that? Leanne, you can pick any number you want between 0 and 2. 1 is good. That's the one I would pick. But if you wanted to make it hard on me, you could pick like the square root of 2, or you could pick 0.11111 or something like that. But no, 1 is great. I love 1. So plug 1 into this thing here, and I get negative 1 squared plus 2 times 1, which is positive 1. And once again, I really don't care about the 1 there. And in fact, you don't even have to write the 1. Just positive. Slope is positive. So things are getting lower, and then they go up. Okay, what happens at 2? That's the next thing. And this is just a minute. Okay. Sorry, it's not doing what I thought it would, but I don't mean anything. Okay, Jarrett, pick a point that's bigger than 2.
I picked 3 and I got a negative.
Oh, you already did it. I was going to do it myself, but yeah, negative. And we don't even care what number it is, do we? Did I do something wrong over here? I guess not. That can't be right. Something is wrong. It's so weird. Sorry, yeah, just because I know what the graph looks like. This can't be what's going on.
Maybe because you're
Oh, no,
saying
no.
threes.
No, it's okay. It's okay. I'm all right now. Sorry. So, wait, maybe what? What did I do?
You simplified the threes.
Yeah, that's all right.
Oh, okay. Yeah, true.
That's legal. No, I'm good. It's the this is actually my first cup of tea that I've had. So I don't know, a couple of cups before I get here.
Couple of cups before you get here?
Yeah, well, I make a pot, and I have to drink the whole thing before noon. So
Why do you have to drink a little bit before that?
I don't know. I'm obsessed. I don't know. I feel like I
What
should.
kind of tea?
It's this. Currently I have Earl Grey.
Oh.
Yeah, a little bergamot in there.
See,
Okay.
maybe we'll share this tea with you.
Yeah, if you come to my office and look at my Rubik's Cube collection,
Okay.
you know you got it. Okay, so excellent. So we're doing well. we have this. So the next thing to note is that that we can tell something about this graph from f double prime. You see, here's the thing, is if I just graph this stuff, oh, I know why I call it critical points instead of critical numbers, is because I want to know the exact points for each of these. So I'm going to be graphing this. So not only do I want to the x value, but I want the y value. So let me get rid of these and do it like this. So I have 0, comma something, and the other one is going to be 2, comma something. Anyway, I could just graph those points. In fact, let me go ahead and do this. When I plug 0 into this original function, I get 0. So there's a point on my graph. When I plug 2 into this function, oh, I get negative 8/3 plus 4, which is going to be negative 8/3, 12/3, 4/3. 4/3. Now there's the point 0, 0, and here's the thing about these graphs, is you don't have to number these like this. 1, 2, 3, 4. In this case, it probably doesn't make sense. In fact, I'm going to do this. I'm going to start here, 1, 2, 3. Now I'm going to be fancy. This is going to be 1, but you don't have to do it the way I do it. It's just I don't want it all scrunched up in a little corner. And so then this is 1, and this is 2. In fact, I don't even have to make my scales the same. I could have, oh, whoa, I know, that was some sort of weird exponential scale. But anyway, I could have, yeah, I shouldn't talk and think at the same time. But anyway, I could have gone like 1/2, 1, 3/2. You don't have to have the scales the same. In fact, if you've done log graphs in your chemistry classes, I don't know if you have or not, maybe not yet. But anyway, you do concentrations and stuff, you'll use log graph paper. And it's just a convenient way to visualize this, you know, with different scales on the different axes. Anyway, getting back to this, there's my first point, critical point. My second point, 2 4/3, actually is right there because of the way I did this. And then I can just draw my graph, right? So according to this, I'm decreasing until I get to 0, then I increase from 0 to 2, x equals 0 to x equals 2, and then I decrease. So let's go ahead and do that. Here, just give me a sec here. Oh, don't copy this down. Trust me. There I've gone down, and then I go up, and then I'll go down. There, that looks great, doesn't it? No, it doesn't. There's a little bit more nuance that we can get from this, from the function. That is not a good graph of this function. I think you probably knew that. Let's get rid of it. So the next thing we're going to do is we're going to look at the second derivative. And the second derivative tells us like the way that the first derivative is changing. Second derivative in this case, let's go ahead and compute this. Oh, you can compute the second derivative and use the thing I have in the box. Don't, yeah, get rid of the 3's. Just do the thing in the box, do that derivative. Well, I'll check to see what else I've got coming up. All right, good. I got stuff. All right, who's got that? Oh, Matt, you got it, don't you?
Yeah.
What's that second derivative?
Negative 2x plus 2.
Negative 2x plus 2. So that's just coming down from this up, maybe, that up there. There you go. All right, very good. So what this tells us is it tells us how the first derivative is changing. This is the change in the first derivative with respect to time or distance or x or whatever it is. So let me switch back to PowerPoint land just for a minute. We're going to skip over that example momentarily and we'll get on to this. So the second derivative actually tells us what's going on with, where is it? Yeah, that's confusing. There. Is that not confusing? Let me see. Graphical interpretation, concavity. Okay, maybe it's better to just draw it. The words are, it's hard. Words are hard this time in the morning, right? It's just going to get worse next year when we go to 7:45 or 7:30 classes. Or is it 7:50? 7:50, okay. prime over change in x. Okay, so that's what f double prime means. It's how the slope is changing as you move from left to right. So here are some examples. When the second derivative is greater than 0, what you're going to see is you're going to see that the slope is getting steeper, getting more positive. So here are some examples of this. Draw this like this. You could have something like this. Notice that my slope is getting steeper and steeper, getting more positive. So that's one example. Another example is something like this. Let's say that we're decreasing slope. If we're going down to begin with, having a positive second derivative means that the slope is changing, but it's getting more positive. So you're actually going to kind of curve like this. So kind of at the bottom of a ski hill. So those are examples of second derivative positive. We've got a name for this. And then this is sort of, to put those two together, this is like the quintessential example of second derivative positive. So second derivative positive means that your slopes are getting, you're kind of curving like this, and we have a phrase for this. We call this concave up. And the reason we say concave up is you probably have heard of the word concave, or concavity is like a hollow or a place that you could press into, like this cupboard here. You can think that my arm is going into the concavity. It's not much of a concavity. It's usually a curved, this can has a concavity at the bottom of it where it sort of pokes inward. So that word, if you haven't heard it before, hopefully you have, but that's what that word means. And concave up just means that the concavity, if you were standing in it, taking shelter from the wind, you're kind of above the graph. So concave up. You might guess that the opposite of this, if the second derivative is less than 0, that means something like this is going on, or maybe something like this, or something like this. And here, this is concave down. Which means the second derivative is less than 0. So second derivative is bigger than 0, you're like that up there. Less than 0, you're like this down here. Okay, so let's get back to our graph. There it is. So you'll notice that I have the second derivative, and in order to figure out what's going on, what we're going to do is we're going to set this equal to 0 and solve it. So I get x equals 1. And we're going to call that point x equals 1 and its corresponding y value, we're going to call it a possible inflection point. Now, I'll show you what an inflection point is momentarily. But for now, let's just say that that's the only place that you could possibly change from concave up to concave down, or vice versa. So that's the idea behind that. So let me get the y value for that. When x is 1, y is 2/3. I can put that on my graph right there. And that's important because when we draw the graph, we're going to want to conform the graph to our idea of this concavity. So let's go ahead and figure out where this is concave up or concave down. And we're going to do the same thing that we just did for f prime. So this is f double prime. I have my possible point of inflection. And I need to pick a point over here and another point over here. And they can be simple or complicated, doesn't matter. But Claire, what point do you want on the left there? X equals 0 is a good one. So x equals 0. Plug 0 into this and you get positive. Positive 2, but it's positive, which means that this is concave up. And then we'll pick a point on the right. Jackson, do you have a point that you'd like that's greater than 1? X equals 2 is a great one to use. Nice, easy thing to plug in there, and you get a negative 2 to be clear, but that is concave down. And then now the point x equals 1 is a point of inflection, because that's where the graph changes from being concave up to concave down. Whenever you have a change like that, that's what we mean. In fact, I should have probably labeled these. This is increasing. This is decrease. Oh, sorry, wrong. Okay, I shouldn't label it apparently. Okay, so let's do this. Now I can draw this thing. So I have to draw everything to the left. In fact, let's go ahead and shade with here. Everything over here is concave up, and everything over here is concave down. So let's see if I can draw this. And they have to meet in the middle. So I'm going to just start at that point in the middle and work my way backwards. There it is. And then I'll start at that point in the middle and work my way forward. Good enough. I suppose there's one other piece of information that we could have used, and that's the intercepts. I believe that this intercept should be at 3. Is that right?
Mhm.
If you set this equal to 0, the original function, you get x equals 0 and x equals 3. Yeah, so I missed that point. But there it is. It's a nice smooth graph. All right, let's see. Do I have a... I see
But we
that...
don't know if it's accurate.
You can... It is... Yeah.
I know, but we don't know the points beyond the things that we plotted.
Oh, yeah. This is... this gives us a guide as to what the graph looks like. It doesn't tell you the exact points, but if you want to know what your graph looks like, that's what it'll look like. If you graph it on a calculator or whatever.
What's the point?
Oh, the point of this exercise is to get us familiar with two ideas. One of them is concavity, and one of them is the whole business of increasing, decreasing, and the maximum points
Okay.
that we will use eventually when we do, what is it called? The whole optimization, which I dropped off the list. We're not optimizing today, but we will next week, not to worry. Yeah, I mean, historically, we did this because we didn't have graphing calculators, and there's a whole art to this. Mine is terrible. Let me go through this. Okay, yeah, let's try another one. And this is going to seem like it's way harder than what we just did, but it is not once we get through our derivatives. So let me find my PowerPoint again. Where is it? There it is. Here it is. Is this it? There it is. Okay. Okay, we did that one. And then we'll do this one. No, we already did that one. So here's what we'll do. Let me copy this. I will help you get started, but then you're gonna be okay. It's gonna be all right. So let me copy this down under F on the next one on your page there. Okay, I'll show you what I've written, and here's what we'll do, is I will help you get the derivatives. So that's critical points, we'll do that in a minute, but let's get the first and second derivatives, and I'll help you if you're stuck on this, don't worry. But let's do this one piece at a time. You'll notice that there's like two pieces to this. There's the 1/5 x minus 4 to the 5/3, and then 2 times x minus 4 to the 2/3. So let's just do one at a time here. So Leanne, we're able to do the derivative of that first piece, the 1/5 x minus 4 to the 5/3? So you could take a guess. Like, I'll just put the 1/5 down, but what do you think happens to the 5/3 in the exponent? 2/3, you said? 2/3, yeah. Very good. Yeah, thought I misheard you for a minute, but no, perfect. All right, very good. We'll simplify that momentarily, but let's get this second one. Now that we got the hard one out of the way, let's do this next one. Raina, can you do that second piece, derivative?
2 times 2 is
Yeah, what's 2/3 minus 1?
Oh, 2/3 minus 1. Oh my gosh, I'm doing it wrong. It's a negative 1/3.
Very
I'm
good.
subtracting it by 2/3. I'm tired.
It's okay, yeah, me too. I should bring the entire pot, maybe, of tea instead of just the thing. Okay, let me clean this up a little bit because it'll help you when you do your second derivative. X minus 4 to the 2/3 plus 4/3 x minus 4. Oh, and I should also mention that lest you worry that we skipped over the chain rule, this is really chain rule, isn't it? I should do the derivative of what's in the parentheses, but the derivative of x minus 4 is 1. So that's why I kind of glossed over that. Maybe I should just put a 1 here to remind us that we actually did do the chain rule, sort of, but the chain rule didn't change anything. Okay, so there's my first derivative. We need to compute the second derivative, and then we'll turn you loose to see how you do getting critical points and so forth. All right, Sam, you're up. What do you think? Second derivative.
I haven't figured it out yet.
All right, well, talk me through this first piece. The 1/3 x minus 4 to the 2/3. What's the derivative of that? Just that.
2/3 x minus 3. Yeah, 1/3 on 2. Parentheses x minus 4 to the negative 1/3.
Very good. And then, of course, we multiply by 1 because of the chain rule, but that just gets lost in the shuffle there. Very nice. So you guys know, it's just scary with these fractional, aren't they scary? They're horrible. But Colton can handle it, can't you, Colton? What about that second piece for up here? What's the derivative of that?
Negative 1/3 times 4/3 times x minus 4 times this expression. And then to the negative 4/3.
All right, very good, very good. And of course, times 1, but chain rule there. Let me clean this one up, and then I'll give you your task for the next 5 minutes.
Yeah, no, I'm great.
Okay, so what we need to do two things that are harder than they were with the polynomials. We need to find the critical points, which is to solve this equation, set that equal to 0 and solve it. And then after we do the critical points, it would be nice to get our possible points of inflection, which is to take this thing and set it equal to 0 and solve. Now, if we can do one of these, I'm pretty sure that the other one will be okay. So let's focus on that first one, the critical points, and see if you can get that solution, or at least get started. And I know what you're thinking. You're looking at this thinking that you have no idea where to start. Well, as long as you use the rules of algebra, I'm just going to copy this and paste it down below so that I have more room to work. You can't go wrong. So as long as you don't violate the rules of algebra, you're going to be okay. So take a guess. Do something. Just do one thing. I mean, if you can solve it, great, but do one algebraic move.
I will do many algebras.
Aha, I do have a plan.
Okay, that's so good. It's good to have a plan. Oh, you've got your plan?
Oh, yeah.
Oh, Gavin, do you have a plan? Do you have anything that we could do algebraically,
I can
even if
help
you think
Gavin
it's
out.
not right?
4. I would make it 0. What? Yeah. X equals 4 would make it 0.
Oh, you're going to plug in x equals 4. That's not really an algebraic move. That's kind of a functional thing.
I didn't say that's how
Not
you do
one of the
it.
answers.
Oh, interesting. Oh, no. X equals 4 is one of the critical numbers, yes.
That's what I was
I'm sorry. I didn't mean to doubt you. You are correct. You are correct. X equals 4 is a critical number, not because it makes it 0 though. So I'll just put this in a little bubble here. We'll get to it. Yeah, if you plug x equals 4 in there, you don't get 0. I know you think you do, but it's not. You don't get 0. What do you get, by the way, when you plug x equals 4 in? You could try it on your calculator. Your calculator will tell you it's not 0. No, don't have. You can just plug it right in. You don't have to distribute. You get an error.
You can do 0 to negative.
Ah, 0 to the negative. It's this thing here. This negative exponent really means 1 over this. And so what Gavin has discovered is the one that I thought we would get at the very end, and that is x equals 4 is a critical number, not because it turns this into 0, but because this is undefined. Nice job, Gavin. Next, let's find another volunteer to find another. Sam, what kind of algebra can you do to this equation? And it could be something simple. You might think, oh, this is a baby algebra thing.
This might be a random, this is just a shot in the dark, but can you use the quadratic formula?
Oh, interesting. You probably could, but I don't want to. So maybe, yeah, I'd like to avoid it though, if that's all right. So no, that's a good, that's pulling some algebra out. That's good. I was hoping for something way simpler than
I
that.
have an idea, Dr. Noonan.
Oh, Jackson's got some, and then we'll come to you. Sorry, actually, he was actually the next person that got picked by the iPhone too. But we'll come right back. We'll see what Jackson has. Jackson, what you got? Multiply by 3. I love it. Let's let's do simple things. You don't have to be complicated. And then I want to see what Jared did. You want to multiply by 3?
It was a convoluted way of multiplying by 3.
Really?
I was gonna put the 4/3 one onto the right side and divide by 1/3.
Hold on.
So you got the exact same number anyways.
No. It's different
How is it different?
because the x minus 4 is on the negative 1/3 one is on the other side. So you got two algebraic things. This is brilliant. We did something simple here, multiply by 3. Then we did something simple here. Move this over to the other side. So there's two things we've done. Now let me do one thing that you might not have thought of, but it is sort of like what Gavin did without knowing. No logarithms. I don't want to get complicated. Come on. 2/3 is equal to negative 4 over x minus 4 to the 1/3. Ooh, cross multiply? Do you remember doing this? Okay, well to cross multiply I have to have a cross, so I better do this. So just in case you don't remember the joys of cross multiplication, here it is. Do this and this. How's that? Okay, so then I've got x minus 4 to the 2/3 times x minus 4 to the 1/3 is equal to negative 4. And there you can combine those exponents and you get x minus 4 is negative 4. And so yeah, x equals 0. Isn't that amazing? All of that, and all we get is 0. No, we didn't just get 0. We got 0 and we got 4. And this is beautiful. Yeah, this is great. Oh, this one's the best one. And yet we can't. Ah, drat. Okay, so just a minute. We need to get right down to the homework preview. We didn't even talk about asymptotes. So give me a sec here. I know, because otherwise you're going to lose your mind when you see the homework. Where is my classes? I need the book. So if you go online, you'll see the homework. And I was told, was it this class that told me that I couldn't have any odd numbers or even numbers?
Yeah.
It was this class, okay.
You just said that yourself.
Okay, well, I forgot. Yes, Gavin?
So how do you get 4 then?
Oh, okay, one way to get it is it's where this is undefined. So where is f prime undefined? And so that negative exponent there means denominator. And so x minus 4 in the denominator, you do what you just did and said, oh, x equals 4, we'll make that 0 in the denominator, and that's bad. Okay, so
If it's undefined, 4 where it equals 0.
yep, that's right. So let me just find, just a sec, this will just take a sec here. Why is this the way, this is even the wrong section, just a minute. We're in 4.3, exercises. Here we are. So I looked in my textbook, it was so lovely. And now I have to actually look online. Here it is. Okay, so I just wanted a simple polynomial. So numbers 9, you'll see online, I don't know what numbers, I can't get Moodle right now, but it's 4.3, numbers 9 and 11, and also, graphs 2. Graph 2. So I just wanted to mention that, and with 9 and 11, they're both polynomials, they're like the first one we did, they're easy. And do the graph as well. The instructions just say to find out where it's concave up and where it's increasing and that sort of thing. Do the graph as well. So that's why I gave you 2 of these, is so that you would have one where you could put your graphs for your homework on. And if you need more of these, I have them online. You can print your own. I know they're not all that great, but there it is. I'm going to stop the stream, the streams of joy here.